Data science is about extracting knowledge from data. Statistics plays a crucial role in this process. It provides the tools to understand, interpret, and make sense of data. Imagine trying to understand a city by just looking at a map of its streets. Statistics is like adding information about traffic patterns, population density, and points of interest. It helps us go beyond the surface and uncover hidden patterns and insights in data. Statistics enables data scientists to make informed decisions, build predictive models, and solve real-world problems. Whether it's predicting customer behavior, optimizing business processes, or advancing scientific discoveries, statistics forms the bedrock of data-driven decision-making. Let's start with some basic statistical measures that are fundamental in understanding data. The mean, also known as the average, is calculated by adding up all the values in a dataset and dividing by the total number of values. This gives us a single value that represents the central point of the dataset. The median is the middle value when the data is arranged in order. It effectively splits the dataset into two halves. If there are two middle values, the median is their average. This ensures that the median accurately represents the center of the dataset. The mode is the value that appears most frequently in a dataset. It helps identify the most common value. For example, consider the following dataset representing the ages of students in a class: 10, 11, 12, 12, 13. This small dataset will help us understand these concepts better. The mean age is calculated by adding 10, 11, 12, 12, and 13. Then dividing by 5, which equals 11.6 years. This gives us an idea of the average age. The median age is 12, as it is the middle value when the ages are arranged in ascending order. This shows us the central tendency. The mode is also 12, as it appears most frequently in the dataset. This indicates the most common age among the students. These measures, mean, median, and mode, give us a basic understanding of the typical age of students in the class. They each provide different insights into the data, helping us to see the bigger picture. While mean, median, and mode provide insights into central tendency, they don't tell the whole story about our data. Variance and standard deviation, on the other hand, tell us about the spread or dispersion of data points around the mean, giving us a fuller picture. Variance measures the average squared difference between each data point and the mean. This calculation helps us understand how much the data points differ from the average value. A higher variance indicates greater variability in the data, meaning the data points are more spread out. Standard deviation is simply the square root of the variance. It converts the variance back to the original units of the data, making it easier to interpret. It's a more interpretable measure of spread, telling us how far, on average, data points deviate from the mean. This can be particularly useful in comparing different data sets. A small standard deviation indicates that data points are clustered closely around the mean, suggesting consistency and reliability in the data. While a large standard deviation suggests greater variability, indicating that the data points are more spread out and less consistent. For instance, if we calculate the standard deviation of exam scores, we can gain insights into the performance of the students. A low standard deviation indicates that most students scored close to the average, showing a similar level of understanding among the students. While a high standard deviation suggests a wider range of scores, indicating varied levels of understanding and performance among the students. Understanding both variance and standard deviation is crucial for data analysis, as they provide deeper insights into the nature of the data beyond just the central tendency. Correlation measures the strength and direction of the linear relationship between two variables. It is a statistical tool that helps us understand how one variable may change in relation to another. It ranges from -1 to +1, providing a spectrum of possible relationships. A correlation of +1 indicates a perfect positive linear relationship, meaning that as one variable increases, the other increases proportionally. For example, if students study more hours, their exam scores increase in a directly proportional manner. A correlation of -1 indicates a perfect negative linear relationship, where one variable increases as the other decreases. This means that if students study less, their exam scores decrease proportionally. A correlation of 0 suggests no linear relationship between the variables. In this case, changes in one variable do not predict changes in the other. Let's say we want to understand the relationship between hours of study and exam scores. By analyzing the correlation, we can determine if more study hours lead to better scores. A positive correlation would imply that students who study more hours tend to score higher, while a negative correlation would suggest the opposite. This insight can be crucial for developing effective study strategies. Understanding correlation helps us identify patterns and make predictions about how variables might influence each other. It is a fundamental concept in data analysis, enabling us to make informed decisions based on observed relationships. Section 5. Gathering reliable data, sampling techniques. In many real-world scenarios, it's often impractical or impossible to collect data from an entire population. That's where sampling comes in. Sampling involves selecting a subset of individuals from a larger population to represent the characteristics of the entire group. Various sampling techniques exist, each with its strengths and weaknesses. Random sampling, where every individual has an equal chance of being selected, helps ensure a representative sample. Stratified sampling involves dividing the population into subgroups or strata and then randomly sampling from each stratum. This is useful when we want to ensure representation from different groups within the population. The choice of sampling method depends on the research question, available resources, and the characteristics of the population being studied. Section 6. Data collection. Surveys, experiments, and more. Data collection is the process of gathering information from various sources. Surveys involve collecting data through questionnaires or interviews. They are commonly used to gather information about people's opinions, behaviors, and demographics. Experiments, on the other hand, involve manipulating variables in a controlled environment to study their effects. They are crucial for establishing cause and effect relationships. Other data collection methods include observational studies, where researchers observe and record data without intervening, and data scraping, which involves extracting data from websites, databases, or other online sources. The choice of data collection method depends on the research question, ethical considerations, and practical constraints. Section 7. Cleaning up the data, ensuring accuracy and reliability. Raw data is often messy and contains errors, inconsistencies, and missing values. Data cleaning is the process of identifying and correcting these errors to ensure data accuracy and reliability. This involves handling missing values, dealing with outliers, removing duplicates, and transforming data into a consistent format. Data cleaning is a crucial step in the data analysis process, as inaccurate or incomplete data can lead to misleading results and inaccurate conclusions. By cleaning and preparing data carefully, we can ensure that our analysis is based on reliable information. Section 8. Painting pictures with data. The art of visualization. Data visualization is the practice of representing data graphically to make it easier to understand and interpret. Charts, graphs, and maps are powerful tools for communicating patterns, trends, and insights hidden within data. Different types of visualizations are suited for different types of data and purposes. For example, bar charts are useful for comparing categories. Line charts are effective for showing trends over time, and scatter plots are helpful for exploring relationships between two variables. Effective data visualization helps us communicate insights to others, identify areas for further investigation, and make data-driven decisions. Section 9. Statistics, the foundation of a successful data science career. Statistics is an indispensable skill for aspiring data scientists. A strong foundation in statistical concepts and techniques is crucial for extracting meaningful insights from data, building predictive models, and communicating findings effectively. Whether you're interested in analyzing business trends, developing machine learning algorithms, or conducting scientific research, statistics will be your constant companion. By embracing the power of statistics, aspiring data scientists can unlock a world of opportunities and make significant contributions to their chosen fields. So, dive into the world of statistics, explore its concepts, and embark on an exciting journey into the heart of data science.